clustering, detecting clusters. So the definition of clustering is to detecting clusters in data. We say in data, but actually in the features, in data's feature space. In the data's feature space, of course, where the data is projected. You're looking for clusters. The approach or algorithms that do that are called the algorithms that do that are called clusters. And there are many, many celebrated algorithms, and more are coming, right? You create one more clustering algorithm, work under some advisor in a university, go get your PhD, one more, right? So lots of creative activity that is happening in this. Now, we will start with what is one of the simplest algorithms. So you ask this question, well, clustering isn't it obvious how to cluster data? It is in computer science, we learn about sorting, isn't it? You can sort data. You see they're unsorted, you can sort data, right? You can search for data, you can sort data. Most of the computer science textbooks are filled with these methods. Why clustering? When you look at data, let's say that I show you cows and ducks. Here we go. I'll take questions in a little bit. Suppose you have ducks, cows, size, and let's say this is weight. Now, the human eye, given this data, how long does it take the human eye to detect the clusters? It is instant. But the eye in living creatures, to the best of our knowledge, has gone through at least 100 million years of learning. So you realize in machine learning, the more data you throw at it, the more time you give it to learn, the better it becomes. The eye is perhaps the most remarkable machine learning tool in our universe that we know of. It has gone through over 100 million years of training at it, and it instantly finds the clusters. It instantly recognizes the patterns, right? Even fishes have eyes. Now, for computers, it turns out that this is actually at least a NP-hard problem. You can't find it exactly. Computers, there is no algorithm that will, in a deterministic way, find the clusters for you. Well, that's a shocker. You would imagine this problem is as simple as searching, sorting, and so forth. Why is it that we don't have a deterministic solution to that? The reasons are varied. Here, I made the clusters very obvious, but let me make it less obvious. Let's say that you're talking about geese and ducks. Let me take two different colors, one for ducks and one for geese. This, let's say that I'm deliberately creating an example that will sort of overlap. Now, how many clusters are there? Suppose you couldn't see the colors. Exactly how many clusters are there? You could ask.
Maybe 7 or 8 clusters.
Right. It is a little hard to tell because you could go making clusters like this. You could say Well, you know what? This is a cluster and this is a cluster too. Or you could say, I see subclusters here. This is a cluster. And I see clusters here, separate clusters here, right? And within the clusters, you may see other subclusters, right? So for example, you see subclusters. Or do you see that the cluster, what you define as a cluster, depends on your optics, depends on the resolution at which you are looking at. Are we together? In the very fine limit, every point is a cluster. And it is hard because of the overlap in data and so forth. It is hard to have a deterministic algorithm for cluster. It doesn't make sense. Common sense way of putting it is, it doesn't make sense because what is missing is what's your resolution and so on and so forth. I mean, many factors. And so clustering is a probabilistic, it's a machine learning exercise, not an algorithm in a typical algorithm textbook, but as a machine learning algorithm, right? So how do we find clusters? Now that we realize that clustering is a little more complicated than we thought, let's look at algorithms to find clustering. So I will mention today 3 classes of algorithms. 2 will cover, hopefully, or maybe only one will have time to cover, but we are going to, in this course, do 3 of them. One is k-means, 2 is hierarchical, what your book calls agglomerative clustering. By the way, this is chapter 10, I believe, in your textbook. And the third is density-based clustering. We'll start with k-means and related. Yeah. So this is what we will start with today. What k-means says, or this family of algorithm, what they say is, suppose you have data, and let's again go here. Now I'll take a whole lot more ducks and a whole lot more cows just for illustrative purposes. And in fact, let me see, let me even erase this. Why am I not able to erase? This pointer has become so big, I can't do the erasing part at all. All right, let's, sorry. Yeah. Let me do. These are cows. Our goal in k-means clustering is to find the center of gravity, to find the 2 clusters, right? Let's say there are 2 clusters. I tell you, there are 2 clusters. We say a k is equal to 2. Somebody has told you privately that, hey, I'm pretty sure there are 2 clusters in the data, right? Your job is to find those clusters, right? And you say, okay, how am I going to find it? The k-means approach is that finding the clusters is equivalent to finding their center of gravity, their centers. Because if you can find the centers, then every point can be assigned to the nearest center, isn't it? So for example, I could just say this, and their center is here. Their center is here. But how do we detect the centers? We agree, right? There are 2 centers. There are 2 clusters. Let me call it C1, C2. But our job is to find the centers of the 2 clusters. How do we do that? And that is the game. And so I will make a lot of diagrams. I don't know, is there a way to copy paste this? But I don't know. Shapes, let me try. No, I don't know how to do this. So I'll keep redrawing this picture over and over again.
Just to right click.
Oh, yes, I seem to have copied. Okay, Control C and right click, copy. And let us go somewhere else. Let us go here and do paste. Beautiful. Beautiful. And I wish I could just erase out the boundaries. With this big fat cursor, it's a little hard.
I think that's when you're erasing, you need to select a larger eraser.
I think so. That may be it. You're right. Stroke, small, large eraser. Okay. All right. We'll go with this. And we will remove the centers also, the highlighting that I did in the center, and I'll bring back the white points. And I'll bring back the blue points. So pay attention, guys. This is a very important thing to pay attention to. What you do, the k-means clustering algorithm, k-means clustering algorithm, it works like this. Initially, you don't know where the centers are. All you know is that we are looking for 2 clusters. Randomly, pick 2 points. So any 2 points, pick, right? And declare them to be the centers. As centroids. Centroid is a fancy way. Just say, think of center of mass. All right. So let us take some points. If we are lucky, we'll end up with 1 point in the white cluster, one point in the blue cluster, randomly, right? But we might not be lucky. We might be very unfortunate. Okay, so let's look at the lucky situation first. And by the way, since I put in so much effort in this part, let me copy paste this because we'll use it again and again. Control C. Control V. Okay, we'll use it later. Let's go here. We will, let's say that we have a lucky guess. Huh? We were good and we picked 2 points. 1 point here and 1 point here, this point. These 2 points. Then what happens? You ask for every remaining point, you ask which centroid it is closer to. Let's say that this is A and this is B. Which is it closer to? And assign it to that centroid. So would you agree that with this, we will end up assigning all of these points to A and all of these points to B? Would you agree with that, guys?
Yes.
Yeah, you would do that. So that is step number 1. So the step is assign, and this is the cycle that you will go through. This is the cycle. Cycle has 2 parts. Assign each point to its nearest centroid, right? And B, recompute the centroid. Centroid is the center of gravity of each cluster. And this is the cycle that will keep repeating, iterative process. So here, if I look at that A, the cluster that is around the point A, would you agree that the center would be somewhere around this? This would be A prime, isn't it? And B, you would go somewhere around B prime, right?
Yes.
And so you would make it, the A has moved to A prime and B has moved to B prime. Now that you have recomputed the center, you repeat the thing. Assign all points to A prime now, A prime and B prime. So you would realize that the cluster remains more or less the same, isn't it? This is a very clean data. It remains the same. And if you recompute the new centroid, will it move? Will it move to some other location now for each of the clusters?
No.
Will it
It'll
remain?
start to
It will
stabilize.
stay. Yeah, it will stabilize, right? So the clusters have, the centroids are very quickly stabilized. This was obviously very clean data and we were in a lucky situation. And do you notice how quickly And so that therefore the end condition is terminate when centroids stop drifting. When they stop drifting, like they may oscillate around a little bit. Wiggling is okay. Let me just say wiggling a bit is okay. Right? So we are done. We just found an algorithm to find the clusters. But you can say, well, you're giving us the best of all situations. Let's take something that is not as pretty.
I think when you said recompute the centroid, what was that? What were we doing?
You take this cluster around A and you find its center of gravity of all the points.
But where do you stop saying it is the zone of A?
The nearest, see, you have this data space, you have data points assigned to A, all the points that are nearer to A rather than B. Each point asks which of the centroids is it closer to. So you would agree that circle refers to all the points that are closer to A, and the other circle refers to all the points closer to B.
Then
recompute the centroid, right? That's recompute the centroid. So that's what you're doing. So now we can say, well, that's cheating. Let me deliberately take some terrible situation this time around. I claim that you randomly picked points and you got A here, and maybe you got B right. What about this point, B? Now, this is about as terrible as it could get, isn't it? What will happen now? Once again, assign to each point, assign each point to the centroid that is there, and you will realize that you will end up with this will be the centroid C1, and this would be sort of the center. I mean, obviously there is not such a big circle. Yeah, even this should not have had such a big arc, but sort of flow with me. Would you agree that if you assign each point to the nearest centroid, either to A or B, it will divide itself approximately like this? Would you agree? Well,
Yes.
you say, well, this doesn't hardly, C1 and C2, they hardly look like clusters, isn't it? They're about as bad as it could be. All right. And what you have done is you have gone straight through the two clusters, right? So this looks like a disaster in progress. But let's see what happens next. You find the centroid of the A cluster. Where would you find the centroid of the A cluster? Would you agree that the centroid of the A cluster will turn out to be at a point like, where should I put it? Something like this. A prime. It can be anywhere, imaginary point. So, and the centroid of B is, because I see more white points, and here there are more blue points, it will be slightly shifted. It will be B prime. Would you agree? Do you notice that in the lower half there are lesser blue points? So it will be shifted slightly. And so now this becomes the new way of looking at it. If you look at this new way and you ask, these points, are they closer to this or that? And you would agree that pretty much, except for maybe 1 or 2 points, B ends up owning this. And A ends up owning, except for some points, maybe 1 or 2 points, but ignoring 1 or 2 points that may be there, ends up owning this. A ends up owning this. Would you agree? So this is your C1 prime, and this is your C2 prime. Do you see that, guys?
It's slowly resolving itself.
It's slowly resolving itself. So it has a tendency to move in the right direction. And so what has happened is that our A has moved to, sorry, what is the journey? Let's look at the journey. A has gone here and B has gone here. Now what happens? The next time you do it, A prime will go where? Would you agree that it will end up here? Because it's the center of this. So this will become A double prime, right? And it will go here. Convince yourself that the next migration of the centroid, A prime will be to A double prime here. Isn't it? Because A is slightly to the right, it will end up owning all the right upper points. B prime is slightly to the left and it will end up owning all that. And so here you will end up with B double prime, right? So B prime migrates to B double prime. Are we clear, guys? Do we see this? Right.
Asif, how do you quantify wiggling? I'm just trying to understand that.
Wiggling is you just set a epsilon. So okay, let me answer your question. Wiggling is you can hand choose an epsilon limit, and you can see if the centroid movement delta of any centroid in an iteration I and centroid I plus 1, the movement of a centroid, let's say A, is less than the distance. The distance that it moves, the delta, or you can say the distance that it has moved, distance between these two, is less than equal to epsilon, you say I stop. So you just set a small amount to stop.
Got it. Thank you.
That is it. In practical terms, what happens is the k-means clustering actually for data that is, most data, it converges pretty fast. There are a couple of pathological cases in which you can get screwed, and I'll mention that. So first thing is that, do you notice that it is remarkable actually how quickly it converges, isn't it? This is lovely. Now comes a question. So, well, then you would say this is a cheap algorithm. Actually not, because every time you're computing the distance of each point from the centroid, and if you're looking at Euclidean distance between 2 points, x1 and x2, right, is equal to, you realize the square root of the distance along each of the axes. Actually, let me write the word x and y so that it's more meaningful. X vector, y vector, then it would be x1 minus y1 square, plus x2 minus y2 square, etc., etc. Basically, you're doing a summation. I'll just put it this way. So the number of dimensions all the way up to plus x dimension d minus y dimension d square. So how many squares do you compute? D of them for every pair of points, isn't it? So it gets computationally a little bit heavy as the number of dimensions grow. You have to do a lot of distance computations. So be that as it may, still it converges pretty fast. There are a couple of pathological cases, and therefore there are many variations of it, of this algorithm. One is this. Suppose data was like this. Now, let me just put it this way. Yes.
For the distance.
No, it is L2 norm. It's Euclidean distance. You can use whatever. So yeah, this is a good question. Which distance should we take? Now we learned about all sorts of Minkowski norms. Pick one. It will lead to its own clustering. Right?
So I was trying to ask the difference between, like, is it a norm or is it a metric? Like in terms of the distance definition.
See, Euclidean distance metric, right, is there, but you can always go to non-Euclidean spaces. Nothing prevents you. So for example, if the data is projected upon a hyperbolic space or something like that, you can use a non-Euclidean metric for distance. So let's say that you have data like this, so this is one cluster, and suppose you have another cluster, And I'm just trying to contrive an example of where these things fail. And let us say that happen chance you pick the initial points to be by bad luck to be this and this points, A and B. Then what will happen is the data will partition itself. Do you see? Equally split itself up and down. And no amount of recomputing the centroid is going to move you away from A and B. Right? It could be, I mean, obviously, imagine it's a dumbbell. Huh? I didn't put enough white points on the other side, but imagine that they do exist. This one also has the same number of points. So imagine dumbbell. You happen to have the misfortune of sitting right in the middle of the dumbbell, both the points. Then your algorithm is not going to move anywhere or ever going to make sense, right? It will stop. It will declare in the very first step that this is your cluster. That's it. These are your two clusters. And you know that they are bad clusters. Intuitively, you can see they are bad clusters, right? So what do you need? What you need are two things. First is you need a quantification of how do you compare to one clustering exercise with another clustering exercise. Suppose in the run one, you do once. So this is the white clusters. And then there are the red clusters, which is this. Clearly, you see that the red clusters are better than the white clusters, isn't it? The white lines is clustering. Would you agree? Right. So, but while it is intuitively obvious, how do we quantify it? How do we know that this time it sucks? So there is a trick. It is a measure of cohesion. See, intuitively, why do we look at the red clusters and call them better? Because all the points are near each other. They are cohesive, isn't it? They're all very near each other. Whereas if you look at the white cluster, many points have vast intergalactic space between them. Do you notice that? There's vast space, vast distances between them, right? There's a lack of cohesion there. And from that intuition, we derive a measure which is called, for any cluster, for a given cluster, cluster Ci, let me just call it Ci, right? So for example, this is C1, C2. What you do is take every pairwise points, Xi, Xj, and compute the distance between them. The square of the distance, Euclidean square of the distance is more relevant. And what you do is you sum over Ij, all pairwise distances you compute. So you realize that all pairwise distances in the red cluster will be much smaller than pairwise distances in the white clustering, isn't it? Right? If you are confused, please speak up, guys. Huh? Think about the white clustering. The white cluster is like this. It is saying that this is a cluster. So this is, if you just join all the points, you realize that there will be some small distances between the points, but there will also be these big guys, right? Big distances between the points that will come up. So your this thing, and then of course you can normalize it by, if you want, the number of points that are there. So this is called WSS, is between one WSS. Well, let me just say within erasing is such a problem. WSS for the ith cluster, right? Cluster. All we are doing is adding up the square distances. And what does WSS potentially, what could it possibly mean? Could you sort of guess its expansion? Yeah, within cluster, some square distances. Of course, you can average it, put 1 over n there outside to average it out based on the points. So within cluster, some square distance. So people, then what happens is, you can say now there are two clusters. So I can find the complete WSS is equal to the sum over each of the clusters Cj, each of the clusters J, like J, the clusters belongs to the set of C1, C2. In this particular case, two clusters, WSSJ. Add up the two WSS, right? So therefore, this becomes if you think in terms of J belongs to C1, C2, and then we can generalize to CK clusters, C K clusters, and summation over and 1 over n is now the, well, okay, you can do all over points, etc. You can do this. Distance is xi, xj within a cluster, xi, ij belonging to, within a cluster. Remember, those pairwise distances are within a cluster, as we just now did, belonging to C, some particular cluster J. Actually, well, I use J here. Let me use, oh boy, let me use K here. Well, CM, M clusters are there. Let's say Cij belonging to CK. Ij, both these points belong to the cluster CK. So in other words, by adding up all of these measures, very intuitively, you can see that it measures the cohesion, right, of the clusters. And this is the measure that you can use. So what can you do? Now, okay, we have a measure, but what do we compare to what? You realize that clustering is sensitive to where the choice of initial conditions, the initial points that you start with. If you're lucky, you'll get good clusters. If you're unlucky, you'll get bad clusters. So with k-means, what you do is you don't trust your initial one run. You run it a few times. You try, do n runs of this training and find the smallest WSS. Whichever cluster gives you the smallest WSS, that is your best answer amongst the 10 runs. Now, in practice, what happens, right, is that you will be unlucky once, very unlikely that you'll be unlucky twice, thrice, etc. Or people often do it 10 times if the data sets are smaller. But if the data sets are ginormous, now you're in a bit of trouble. You suppose if the compute time of this, right, is a giant space that will take 3 days to do. You don't have the luxury of running 10 runs, right? Or running, unless you have infinite hardware, 10 runs in parallel. So people do all sorts of tricks. What they do is they do this. One trick is some modifications they do on the base algorithms. So these are all modifications. I'm just mentioning it to close the chapter on this. Is what you can do is when you choose a random point, let me just call this random point x0, right? For point A, the initial point, and x0b. By 0 here, I mean the initial point. What you do is go back to this cluster in such a way that let's go back to our two clusters. What you do, let's say that you randomly happen to pick this as your first point. I'll just take this example. What you do is you search for the point farthest away from it. Right? The farthest away point could be possibly this point. Does this look reasonable? Right? Far away point. You take a far away point. So if this is A, you make the far away point B. If you're looking for 3 cluster, you will find the point farthest away from A and B. Now, right? And so forth. You'll continue along that. So then you realize that you're much less likely to be in a pathological situation. Very likely you'll converge onto the best cluster right away. Am I making sense? You know that this will quickly converge to this A prime, and B will quickly converge to B prime. Right. So this is one thing that people do. So there are all sorts of adaptations of k-means and tricks people use in implementation. One moment, I'll come to questions. The second thing that people do when they do is, see, you have to assign point by point, each point to a cluster. Now, which cluster it belongs to. Now, there are geometric arguments. One of the earliest one was the use of structures called KD tree. We won't talk about it now, but we'll talk about it in engineering math. KD trees and its generalization are called metric trees. What they are, roughly speaking, is they take the entire feature space and hierarchically divide it based on some distance metric. Right, some distance metric, such that when you do that, in each subregion there are a certain number of points, and you don't assign each point to a centroid, but you bulk assign an entire region to a centroid easily. Are we together? You can bulk assign a region to a centroid quickly, and that makes it much faster. This creates accelerated versions of k-means clustering. In practice, that's what you do. If a metric is available and can be constructed, you do some sort of optimization like that, and the acceleration that comes about from that is of course tremendous. But the cost is that you have to first build that metric tree, or the KD tree, for example. Commonly, you have to sit and build it on the data space. So you do it in two stages, right? That is it. Now, I will take questions in a moment, but I want to finish the train of thought. There is one thing I left out. Without seeing the data, how do you know what is the best K? How many clusters there are? That question remains to be determined, right? K-means clustering algorithm answers only half the problem. It says, tell me how many clusters you want to find. And no matter what number you give it, as you will see in the labs, it will go and find exactly that many number of clusters. But that number may be wrong. For example, in this data sets of cows and ducks, suppose I find 4 clusters. Now, how do you find 4 clusters in the data? It will artificially go and find 4 clusters, right? It will end up dividing your cows and your duck clusters into 2, most likely. Isn't it? So it will do that, and you know it isn't the best way to go about it. So that brings us to the question, what is optimal K? K is the hyperparameter of the model, isn't it? K, the number of clusters, is a hyperparameter of the model. Let me write that thought down. What is the optimal number of clusters? And the answer to that is quite interesting, actually. For us to find, so this becomes a hyperparameter of this k-means clustering. How do we do that? So what we know the WSS, the best WSS for each value of K. What we can do is we can start with K is equal to 1, K is equal to 2. Why K is equal to 1? It may be true that the data is just one cluster. You don't know, isn't it? One cluster may be it. K is equal to 2, K is equal to 3, all the way. K is equal to the number of data points itself. Of data points itself. Now, what you do is you create a table. You say K, and so 1, 2, 3, 4, 5, and you put WSS. Now, what would be the WSS associated with K is equal to N? 0, exactly. And the K is equal to 1. If you look at the cows and ducks, you can imagine looking at the cows and ducks, the WSS will be pretty appreciably large, isn't it? Right? Because they are really 2 clusters. And so between them, there is a lot of, what do you call, sort of, if you think of them as galaxies, there's a lot of intergalactic distances, right? So you start with WSS 1, for the value 1. And so you come with this. And then what you do is, it is called the elbow method. The elbow method. Now comes the formal name is scree plot. So look at me, if you guys will look at me remote and so forth. This is my hand. Do you see that the bend in the hand, the most pronounced bend is where? In the elbow. Either it is straight and there is no bend, or the most pronounced bend is at the elbow. So what you do is you take the data for k is equal to 1, 2, 3, 4, 5, 6, 7, all the way to n. What you do is you start with WSS here. What will happen is, let's say in this situation, WSS rises to this. You know that after this, in the case of cows and ducks, the more clusters you choose from, the more it keeps going down, and ultimately it will go down to 0. This will be the graph of WSS for a given value of k, isn't it? This is k. Would the WSS values look like this, guys? At every increase in k, you will get smaller and smaller clusters by definition, right? And so your WSS will look like this. Plot of WSS will look like this. First, take a few seconds to convince yourself that this is how it will look. Right? It may not have this pronounced bend. For example, it could have a bend like this, like this, but at some point it will have a bend. Either it will be a straight linear decrease or it will have a bend. You agree with that? When there is a bend, look for the elbow. Where is the elbow here? At which value of k? Anyone?
2.
2. It's at 2. So we say that because the elbow, we found the elbow. So we say that what your scree plot, what your elbow method is telling you is that the optimal k is equal to 2. Are we together? This is your best k. And that's how you detect that's how you find the best value for the hyperparameter k. So now I would like to summarize this and then I'll take questions. This was a very interesting way to cluster data. It is perhaps the oldest way. In k-means clustering, the main steps are randomly pick centers. I've done it for 2 clusters. Now you can generalize it to 3, 4, 5, whatever you want, or pick those and declare them to be the initial centroids. Assign each point to its nearest centroid. So now you have clusters, right? A centroid and all its associated points make a cluster. You have found 2 clusters. Now of the cluster, don't trust it yet. Recompute the centroid of each of those clusters and mark them as the new centroid. And then reassign points to the nearest centroid and keep repeating, keep doing it in a cycle. Terminate when the centroids stop shifting, which means that drifting. In other words, a little bit of wiggling is okay, like within some distance. If it just wiggles, the nature of probabilistic methods is when there's noise, they'll always drift a little bit. What will happen is some points will keep just oscillating, changing loyalties. There's sort of the people, what are these important points? In 2 political countries which have 2 political parties, usually there are some people in the middle. Every election they change sides. So sort of like that, right? They might keep changing.
Swing voters.
Swing voters, exactly. And so there may be some swing voters in between. And so there may be a bit of a wiggle room. But you can stop at any point because you're not looking for perfection. You're looking for effective answers, effective clusters. You stop. That is your k-means clustering algorithm. Now, just on this point, do we all understand it, or is there any ambiguity or anything I need to clarify of what the algorithm itself is? Right. Okay. So then we'll go to the next stage. You see what is the distance measure? You take Euclidean or any kind of a reasonable distance measure. You can even take non-Euclidean distances, very easy. You can go with all sorts of things, metrics. We need a measure.
Question.
If you try different distance measures, would the speed plot differ and you would get different?
Yes, of course. Your notion of distances matter.
It
They
doesn't-
matter. Because distance is distance. Like, for example, how far, so I'll give you an example. How far is from me to there, Abhijit, right? Well, it is as the bird flies, or it is like, then finally there, right? So then he is, how far is he compared to, let's say that I don't have to do that to go to my room. Then it suddenly looks that my room is much closer to me than Abhijit is. So how you define, the word is geodesic. The distance between 2 points in any given any metric is the geodesic.
So then if somebody asks you to partition, then this should also give you a measure, right?
Yeah, implicitly, you always have a measure. That is one of the things. You have to, first thing you do in your mind is pick a measure. Most people pick Euclidean, but you shouldn't. I'll give you an example. What is the distance from here to India? The shortest distance is you go straight through the earth, right? So all distances are basically only about 13,000 kilometers. But if you fly with an aeroplane, you can't actually go bore straight to the center of the earth. You have to fly around it. So implicitly, the distance is non-Euclidean distance, right? It's a geodesic, or what is called the great arcs. So the shortest distance, and as you know, it's approximately 18,000 kilometers, not 13,000 kilometers. It comes because you have to fly on the surface of the earth, over the surface of the earth. So distance definition is central to all of this.
I have a quick question.
Please go ahead.
So hypothetically speaking, if the data is close to being linear, then how would you cluster it?
By linear, you mean uniformly spread out?
Yeah.
Yes. Okay. So hold that thought. I'm going to answer that for you. Huh? So no.
Okay. Yeah.
Hold that. So, but let me just review that. But that's a very interesting question you asked. Now, we understand what WSS is. It's a measure of cohesion. It's just within the cluster what are a pairwise distances squared. Squared because it's a nuisance to look at square roots, right? And a square also amplifies for the same reasoning that we did some squared errors. It amplifies what? Large distances, right? It escalates or makes them stand out.
So when you say for this cluster, but we don't know where this cluster is ending, right, at this point, because
No, you don't do that. See, in k-means clustering, what you do, so that is another point. So hold that thought in your mind. Where does the cluster end? That second question we'll do. But let's just review it. Then we'll answer it one by one. Actually, please give me 2 minutes. I'll drink some water. Huh? Right? So on and so forth. See, ultimately, the results you get is based on your initial setup. When you set up an experiment, you decide what your feature space is, and you decide what you're going to look for, and then you go looking for it. And the results you get depends on that.
Whereas going with that is, if I chose, let's say I want to see how many Abhijits are there, how many Premjits are there in that group, and that's why I chose name. Then I do that, my distance functions will be completely different from had I gone with weight.
Yeah, in fact, distance function would be just binary. If the names match, distance is 0. If the names don't match, distance is 1 along the distance axis, right? That's it. And you use that because you can't argue that Abhijit is closer to Banerjee, but further away from Karthik. That wouldn't make sense.
So that has to come from the domain. The domain has to specify.
Domain has to tell you what it is, right? That's how it is. So in all of these k-means clustering, all clustering algorithms, one of the most important thing is what is your metric for distance? And surprisingly, that is often the secret sauce of companies. People spend, learning a good metric itself is a machine learning exercise. Here we are learning to, walk first. We are learning, assuming sort of, okay, let's take Euclidean metric and let's run with it and so forth. So we get the basic idea of clustering, but life gets more interesting when you ask, okay, what should be my metric? And especially for people who have done search engines and so forth, often the metric is the secret sauce in many situations. You don't want to reveal that. You learn that.
Asif,
The street plot, when you get that optimal n, right? Is that n indicative of the number of dimensions in which actually the data?
Nothing to do with the dimension. Nothing to do with the dimensions. It has only to do with what is the best number of clusters k-means clustering can find. That's all.
But nothing to do with.
Nothing to do with the dimensions. Somebody on the on Zoom had a question.
yes, Asif, can you go to the plot of that n? Like you started from 1 to n, right? So you said like the competition here is quite heavy. I mean, it gets compute heavy program. So in practicality, like we'll start maybe with k equal to 1, compute for some time, k equal to 2, 3, and then make a decision if you find the elbow or not.
The moment you find the elbow, see here what I would do is, by the time I reach k is equal to 4, I would say no point moving further. I already know my answer. So what people do in these, sorry, I'll just sit down, I'm a bit tired. So can you guys see me?
Yes.
Yeah. What you do in real life is, first of all, the very first time you do these computations with the data, you don't know what the optimal k is, right? So for example, these things are typical exercises inside Facebook, etc. You have a giant social graph, you're trying to cluster, you find the groups and so forth. So you don't know, but after a little while, what happens is, you know it. So k today and k tomorrow are not going to be terribly different the next time you do the clustering. So you already know what the ideal k is, and you just search around it. That did it drift? Did the value of k change in the last month or in this, right?
Okay.
But you don't go and search, like ab initio means you don't know, right? In the first day, you have to try a lot. So in practical terms, you don't have to. The second point that I made is that, the number of tries. People tend to, like, for example, when you run this sklearn, scikit-learn, it will ask you how many number of tries, otherwise it will assume. But in reality, what happens is, people use other optimizations, like for example, taking the furthest point. They know that it worked on the data once, the data will only slowly change. So it must work on the data the next time they do the same exercise. So in real life, now you learn a lot from experience, and you use that to decrease the amount of computations you have to do.
Okay, so if we just like, I want to calculate maybe some rough estimate, like my data points change from million to 5 million, and my optimal k was maybe 6. If I want to recompute everything,
Probably between 4 and 7, 4 and 8 at most.
Okay.
That is most likely it is between 5, 6, 7. That's it. Right.
Okay.
And the most likely situation is if you're just going from 1 million to 5 million, you will find that your optimal value is still sitting squarely at 6.
Okay.
And the other thing is that how much of a degradation there is if you stick to 6, right? See, one of the things is you found 6, you're going to cluster by 6. Your data changes, data pattern changes.
Yeah.
So it is called model decay. Your model has decayed. The reality has changed. The shape of the clusters have changed. But how much change is acceptable and how much is, at what point do you say that now it's screwed up? Generally, in practical life, a little bit of decay you tolerate because it's still working. And the computations are expensive if you're doing big data computations, right? So you wait for a little bit and then you recompute.
Okay. Okay. Got it.
Asif, what was the first modification to k-means?
The first one is saying that when you take the initial points, you said randomly pick 2 centroids, 2 points, and declare them to be centroids. The trouble is there could be pretty bad choices. So what you do is you take a point randomly, and the second point you take to be as far away from the first as possible.
Got it. Okay. Thank you.
Right? And then generalize it to 3. So suppose you have to find 3 clusters. You find a point furthest away from it, and then you find the third point which is furthest away from both. Right? And therefore you can keep generalizing to k clusters. That's what you use. And the other optimization is instead of assigning 1 point at a time to a centroid and finding it out and computing, which is brute force, you can use the geometry of the underlying space. You can use these things like KD trees or metric trees. They are ways of subpartitioning the space into rather more granular, more sort of a coarse-grained, more bigger boxes, bigger regions, such that each region, you don't compute it for each point, but for each region. And you know with confidence that if I can assign this entire region to this cluster, right? So to this centroid. So
Looking at a block rather than.
block, exactly. In the California data set, it's almost like looking at a block for median income, etc., rather than each house. Right? So that makes the process run much faster. All right, guys, so we talked about k-means clustering. I noticed that we are running out of time. It's going to be 1 o'clock. We have a choice. In the afternoon, we can go into another algorithm, which also will be intense. But I think maybe is this okay? Are you all fine with Tuesday? Maybe let's do it slowly and properly. So let's keep it for Tuesday for the second one and next week for the third one. These are all big topics. Let's understand them properly. We have another 6 minutes. Any more questions before we break for lunch?
So, Asif, so if I'm looking at if my value is smaller, so does this mean I'm seeing the global structure? And if I take my k value to be higher, like I see a smaller cluster.
That is right. The bigger the
k.
k, the bigger the k, the smaller the resolution. The more close you're finding subclusters.
Okay, so it's kind of balancing between the local and the global structure.
Exactly. That's what you're doing.
So that's where the concept of that UMAP came.
UMAP is quite related to that, but it is an idea coming from the. See, UMAP is a way of projecting data into lower dimensional space by looking at manifold embedding, right?
Yeah.
Which is a topic, again, a lovely topic for math class, not for here, because now I have to explain what a manifold is, right? Not for now.
Okay.
And those of you who are taking, this is a first encounter with machine learning, absolutely ignore all of these tangential questions. Don't be worried about it. First, let's get your foundations right. Then when the time comes, you will learn all of this in the next course.
It's a more of a general question, right? So clustering is an algorithm that we're learning right now. When you're approaching a segmentation problem.
Segmentations are clustering problems. Market segmentation, almost always clustered. For example, your t-shirt sizes are determined. How did you come up with small, medium, large, extra large, 2XL, etc.? Clustering.
So
data clustering.
segmentation.